In this video, we're going to talk about some basic principles of data communications. We're going to concentrate on carrier waves, talk about analog and digital signaling, and talk about how various aspects of a carrier wave can be manipulated in order to embed or encode digital data within that wave. And therefore, as that wave propagates through some transmission medium, that data can be transported from one place to another. Okay, so the first thing we need to talk about is the concept of a sine wave and its rather fundamental relationship to data transmission. Okay, when we transmit any sort of energy through a communication channel, and that energy could be in several forms. We could be talking about light, as in laser light transmitted through a fiber optic cable. We could be talking about electricity transmitted through some kind of copper wire. We could be talking about radio frequency waves broadcast through the atmosphere or through outer space. We could also be talking about audio waves transmitted through the atmosphere, or sound waves if you like, although since sound is not usually used as a data transmission medium for or data transmission method for computers, I didn't list it here on the slides, but we are going to do some sound-based examples a little later. So on the right we have a graph which shows a typical sine wave, and there are various characteristics of this sine wave that can be manipulated to embed data. The first is its frequency. Notice that the wave starts out at a zero value, has a gradual rise to some maximum positive value. This is its maximum energy state. Then has a mirror image descent back to the zero value. And then in essence, if you look at the left hand of the diagram and just kind of flip it top to bottom, you get the right hand side of the diagram where there's a gradual descent to a negative energy state and then a mirror image rise back up to the zero state. This is called an oscillation. So we oscillate between positive and negative energy values, okay, always starting and returning to that zero value, okay. And that change, that gradual rise and then fall and then rise again, occurs over a period of time, okay. Frequency is a measure of how often this curve repeats over time, okay. We call each of these, we call one instance of this starting at a zero, going to maximum, down to minimum, and back to zero. That's one cycle of the wave. Okay. And frequency is simply how many cycles per second occur in this wave. Okay. And we measure that in something called hertz, which literally means cycles per second. Okay. And is abbreviated as Hz, where the H is always capitalized. Okay. In electricity, we don't really have anything we can, detect as human beings easily to notice what the frequency of an electrical wave is. In the case of light, if we're talking about visible light, then we do recognize frequency. We recognize it as color. Okay. So, for example, blue light has a higher frequency than red light, and the various colors of the spectrum fall somewhere in between in those frequencies. Okay. In the case of sound, we recognize frequency as pitch. So low frequencies would be a very low. My voice doesn't go very low. Whereas high frequency would be something like that. Okay. All right, so that's the first aspect of a sine wave that we could manipulate. We could change its frequency. Second thing we can manipulate is amplitude. And amplitude is basically what is this maximum positive and negative state. And note that the maximum positive is always the same as the maximum negative, at least as measured as distance from this zero value. Okay. And basically amplitude is a measure of power. If I put more power into the signal, then this rise will go to a higher value and this fall will go to a lower value. Okay. So more power corresponds to greater amplitude. Okay. In the case of electricity, I guess you could say we could detect that, since low power, if we were to touch the wire and accidentally ground ourselves, might give us just a tiny little shock, whereas high power might give us a very big shock. Okay. In the case of light, it's simply the intensity of the light. Okay. A very bright light would, like say sunlight, would have very high power and have very high amplitude, whereas say a very low intensity light, like what you get out of your flashlight when your batteries are nearly dead, that would be low amplitude. With audio signals, amplitude is basically volume. Okay, so low amplitude would correspond to something very soft, whereas or high amplitude would correspond to something very loud. Okay. The last characteristic, and this is a rather different characteristic from the first two, is something called phase. Okay, and as I look at this axis down here on the bottom, where I just have time 0, time 1, time 2, time 3, time 4, let's say maybe these are, I don't know, quarters of a second or something like that. So this is 0 seconds, this is 0.25 seconds, this is 0.5, this is 0.75, and this is 1 second. Okay, so we've got a frequency of 1 hertz here, 1 per second. Okay, 1 cycle per second. Phase is a measure of where on this variation from peak to trough back to 0 we are, and it's measured in degrees of a circle. And that may sound rather strange, but I'll show you why that is in just a second when we click on this link. So 0 degrees, okay, or 360, depending on your point of view, is where the 0 value is. It's where the wave's energy is at 0. It's neither heading up, it's it's not positive, it's not negative, it's right at 0. The 90-degree phase is where the maximum positive energy value exists. The 180 is where we sit after we return down from the maximum positive and right as we cross the 0 value. Okay, the 270 is at the negative peak of amplitude. Okay, and then the 360 or 0 again is once we return back to the 0 state from the negative peak. Okay, so let's take a look at what's in this link, and I've already opened it up in a web page here. And that'll bring you to this. Think of this red dot here as a flashlight. Okay, so you got a flashlight and it's shining this beam of light, which is the gray here, and then this dark red spot is what's showing up on the wall. Okay, and if you were to move this flashlight around in a circular motion, but keeping it pointed at the wall, okay, and let me start this play so you can see that. Actually, I think I just want to refresh this. There we go. Notice that spot on the wall goes up and down and up and down and up and down. It does so in a very smooth motion. Okay? And that motion is in fact very similar, or is in essence the same really, as what we have plotted here in this figure on the right. Okay? Now if I move forward here, what does this have to do with a circle? Well, note I'm moving this flashlight around in a circle, and like any other circle, we can measure the position along the circle in degrees. So if the starting point here is 0, then that would be 90, that would be 180, that would be 270, and that would be back to 0. Okay, so I'm going to call them out as we run this. Okay, so there's 90, 180, 270, 0. 90, 180, 270, 0. Okay? Looking again back here. 90 was the maximum peak. 180 back to 0. 270 was the negative peak. 360 or 0 back to the starting point. Okay? Now, if we were to plot this, which is exactly what that figure does, we wind up with this diagram right here. And there's another example of a sine wave. Okay, so this is simply plotting that motion up and down the wall on a timeline where this x-axis represents time. And that's how you get the classic diagram of a sine wave. Okay. Now, it's not really covered much in the textbook, at least not at this point, but I do want to make a point here. A sine wave is an example of what we call a simple or a fundamental signal. Okay, and taking the audio example, unfortunately I don't have an audio sine wave signal that I can play for you here, but it's just a pure tone. It's like a synthesizer with no effects and nothing fancy added. It's just a very pure tone. Most signals in the real world, be they audio or light or whatever, are complex. Okay, They don't contain one sine wave of one amplitude and one frequency. They contain a bunch of different sine waves added together, and those sine waves may have different frequencies, different amplitudes, or both. Okay, they may start at different phases and get combined together. So sine waves are a good starting point for talking about signals, but realize that most signals in the world are complex. For example, let's take sunlight. Okay, sunlight, as most of us, at some point in elementary school, probably played a little game where we took sunlight or took, some white light source, shined it through a prism, and out popped all the colors of the rainbow. What that was showing was that the light that was going into the prism was a complex light signal, which consisted of basically the addition of all of the colors. Okay, so white light is not white. White light is the sum of red and green and blue and yellow and orange and all the colors in between kind of added together in order to generate white, quote unquote. Similarly in, audio signals, okay? When you go to listen to a band, you're not just hearing one sine wave, okay? I mean, if we can, for a moment, think of each instrument or each voice in the band as a single sine wave, if there's a voice and 4 instruments, well, then we're getting 5 signals added together. Well, the reality is each of the individual signals is not a pure sine wave. Your voice is not a pure sine wave. When your vocal cords vibrate, they generate lots of different signals, and the sound of your voice is essentially the addition together of all those signals to produce one complex signal. Likewise for a piano or a flute or a guitar or a drum kit or just about anything else. Okay, so my point here, and we'll get to this in okay. So looking a couple slides forward on this example one here, the pure sine wave here we're talking about is the fundamental, okay, but there's other possible waves that could be added to it. In this case we have something called a second harmonic, which is at double the frequency, and we have a third harmonic, which is at triple the frequency. So think of 3F, 2F, and F on this diagram as 3 different pure sine waves, which if I add them together, okay, gives me a complex wave as shown here at the bottom. Okay, so note that the wave labeled F is a pure sine wave. The wave labeled 2F is a pure sine wave with lower amplitude but higher frequency. The wave labeled 3F is also a sine wave with even lower amplitude and higher frequency. And when I add those together down here at the bottom, what I get is a wave that is not a sine wave. Okay, I'm not sure how you would describe this, but it is not a sine wave. Okay, and clearly, as I would add more sine waves of various types to this, I could get even weirder and weirder shapes. Okay. So my point bringing this up now, and we will return to this later, particularly when we talk about square waves and purely digital transmission, is that the energy we push through a transmission medium, be it electrical channel, optical channel, acoustic channel, or just about anything else, rarely contains pure sine waves. Often it contains complex signals, which can be thought of as a summation of a bunch of different sine waves. And each of the individual components can be represented as a sine wave, but once they're added together, we get something that's not a sine wave. Okay, enough beating that one to death. Okay. So, thinking of this pure sine wave for the moment, okay, as something we're going to send through this, through this wire or, through this fiber optic cable or whatever it is, okay. That is something we would call a carrier wave. Okay, so imagine for a moment, let's say we're talking an optical channel. We're going to produce pure green light, for example. A single frequency using a finely tuned laser that's going to generate just green, not blue-green, not, brown, just pure green, okay? So our basic wave going through that fiber optic cable is a green sine, is a sine wave of optical energy, and its frequency just happens to match green, okay, and its amplitude is whatever power, however bright the laser is, okay, that we're pushing through there. So, okay, so you got green light coming through there. Well, what good's that do us? Okay, so yeah, I could shine it on the wall, and that looks kind of cool. I got a green spot on the wall. I put it in a little handheld laser pointer, and I can play games in the middle of class while the teacher's trying to talk. But how do I use this to send data from one place to another? Well, now we're going to rename this. Okay, that pure sine wave, which is green light in this example, is an example of what we call a carrier wave. Okay, and so what we want to do is, instead of sending that pure green light with exactly the same frequency and exactly the same amplitude, smooth variation in phase, okay, from one place to the other, we want to vary one or more of that wave's characteristics, either frequency, amplitude, or phase, and as we'll see later, maybe 2 or 3 in combination. We want to vary those to encode bit values. Okay, remember, bit values 0 or 1. Okay, so that's the basic idea behind data transmission. Take the fundamental carrier wave and vary something to represent zeros and ones. Okay. Now, before we move on to talking about how we do that varying, let's talk about the various ways these waves can get from one place to another. Okay, one possibility, electrical cables. Okay, that could be Ethernet cable, classic twisted pair. That could be coaxial TV cable. That could be lamp cord. That could be just about anything else. Optical cables. We'll talk later about the various types of optical cables, but for the moment, just think a glass fiber that can carry light, visible light, from one place to another. Well, those are examples of what's called guided transmission. What if, hey, this is the modern world. Isn't everything supposed to be wireless? Well, fine. Let's use radio frequency waves, okay, which is basically just electrical energy or electromagnetic energy transmitted through space, okay. So wireless Ethernet, FM radio, broadcast television, those would all be examples of radio frequency transmissions. And the fourth example, as we did last time that I didn't leave off here, there's sound. Okay, acoustic energy transmitted through an atmosphere. Okay. So all of those can be ways of routing a carrier wave from one place to another, either in a guided sense with cables, or in an unguided sense, such as with radio frequency or such as with audio. The same basic principles apply to all three, or all four in this example. They all have sine waves going through them. Those sine waves can be considered as carrier waves, and we can encode data within the wave by varying frequency, amplitude, phase, or some combination of the above to represent bit values 0 and 1. Okay, so let's talk about each of these things that we could vary. First off, realize that the typical word we're going to use for this is what's called modulation. And now in electrical signal theory, modulation has a very specific meaning, and I'm using a little more generally here. But there are we can modulate or vary, if you like, or control, if you like, the size of the peak of the wave. Okay, and if we're talking about a pure sine wave, that's called amplitude modulation. If we're talking about embedding digital data in it, typically we're gonna call it something. We're gonna call it amplitude shift keying. Okay, but in either case, what we're doing is we're using amplitude or power of the carrier wave to represent something. Okay. Over on the right, I have a very simple example here. Now, of course, hardly anybody talks about Morse code anymore because, radios have gotten so much better that we don't, people don't transmit data using dots and dashes anymore. They transmit data using voice. Okay. But in the bad old days when there was Morse code, we transmitted dots and dashes. As generally, we transmitted the dots as a short burst and a dash as a long burst. So it was, SOS is dot, 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 dash, 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 dot, dot, dot. So we would do 3 short acoustic signals followed by 3 long acoustic signals followed by 3 short ones. Okay, but we could have just as easily done it using amplitude, which, if we were talking about an acoustic signal, would be volume. Okay, so a dot could be a small amplitude, whereas a dash could be a large amplitude. Okay. Using that same sort of thing, we can embed bit values. Okay, so if we think a dot is a 0 and a dash is a 1, okay, here's a byte, okay, containing 8-bit values. Okay, here's a carrier wave moving through over time. Okay, and what I'm doing is I'm varying the amplitude here to represent ones and zeros. And what I'm saying here is a binary 0 I'm going to represent as 1 volt held for 1 wave cycle. Okay, 1 full 360-degree movement. Okay, a binary 1 I'm going to represent as 10 volts for 1 wave cycle. Okay, so this first one here is a 1 because the peaks are 10. This second one, the second cycle here represents a 1 because its peaks are at 10. But this third cycle here represents a 0 because its peaks are only at 1. Okay, so what would the receiver see? Well, at the other end, assuming that I sent this carrier wave and was varying the amplitude to represent 0 and 1 according to this encoding scheme. Okay. Well, it would depend on the type of it depend on the type of signal. In the case of electricity, I would get 2 bursts of high power followed by 1 burst of low power. Okay, and if I had some sort of device that could detect voltage variations and say switch on or off, if 10 volts was received, then that would recognize those bits. Okay, if this was optical energy, this was light, then these first 2 bits would be very bright, whereas this second bit would be relatively low power, relatively dim. Okay, if we were talking acoustic energy, these would represent loud sounds, and these would represent softer sounds. And I actually have a little example here, which I'm going to kick up here in a second. Let me pull this up. And let me also open up the audio mixer here. Okay. So what I've done, I recorded just a piano sound, playing these as acoustics, as piano notes. Okay, it's the same note in each case because note the frequency is the same. Okay, what's going to be different is the volume. So let me go ahead and play this sequence of 8 bits as an acoustic signal. Okay, using amplitude modulation. Okay, so there's your 8 bits. Okay, let's run it by again. Okay, 1, 1, 0, 1, 0, 0, 0, 1. And let's look down here at the bottom. If you look under the Windows Media Player or the speakers, watch the green that goes up and down with the volume, and note the change in the height as we move from the 1 bits to the 0 bits. Okay? So, whether we're talking electricity, whether we're talking light, whether we're talking radio frequency energy, or whether we're talking sound, the principle is the same. I'm going to use high amplitude to represent a 1. I'm going to use low amplitude to represent a 0. The absolute values of high and low are not particularly relevant as long as whatever's at the receiving end can distinguish between those 2 values and recognize them as high or low, and therefore 1 or 0. Okay, quick question. How many bits per second can be transmitted using the encoding method we just went through on this last slide? Okay, this one right here. How many bits per second? Okay. Well, there's a 1 bit, there's a 1 bit, there's a 0, there's a 1, there's a 0, there's a 0, there's a 0, there's a 1. We've got time here, but we don't have units of time. So how long is this 1 bit? Well, it depends on the frequency of this wave. Okay, if this is a 1 hertz wave, in other words, if this time mark right here, let's do a little, if this is 1 second, and this is 2 seconds, and this is 3 seconds, and so on and so forth, okay, in other words, this is a 1 hertz wave, well then basically I'm sending 1 bit per second. In the first 1 second, I sent a 1 bit. In the second time, the time period between 1 and 2, I sent another 1 bit. In the time period between 2 and 3, I sent a 0. Okay. So, how could I make this a little bigger? Or how could I make the data transmission capacity of this a little higher? Well, I simply use a higher frequency wave. Okay, where instead of this cycle taking a whole second, now maybe I say it takes a millionth of a second. Okay. So if this elapsed time from here to here is 1 millionth of a second, okay, then presumably I can have 1,000,000 bits per second transmitted. The bottom line is the answer to the question of data transmission capacity boils down to the question of what is the frequency of this wave. Note I haven't changed the frequency here, I've only changed the amplitude. The frequency is constant. Okay. So, answer, it depends entirely on the wave frequency. Okay. Single bits encoded in each wave cycle, so the question is simply how many wave cycles per second. Okay. If I was using, say, a 50 megahertz, 50 million cycles per second carrier wave, then in theory I could transmit 50 megabits per second, 50 million bits per second, using the method we just went through. Now note, that's in theory, okay? That's best case, if you like. There are practical considerations that could make my actual transmission rate substantially less than that, okay? But in theory, a 50 megahertz carrier wave is going to get me 50 megabits per second using this method, which encodes 1-bit value in each wave cycle. Okay, that's the key takeaway from this particular example. So now let's move on to another way we can encode data in a carrier wave. As we've already seen, we could manipulate the amplitude, but in addition, we could manipulate the frequency. And this goes under a couple of names as well: frequency modulation, or if we're talking purely digital domain, frequency shift keying. Okay, the idea here is, well, when we did amplitude modulation, we kept the frequency constant but varied the amplitude. Now we're going to do the opposite. We're going to keep the amplitude constant. Note that all these peaks here are tens and negative tens, but we're going to vary the frequency. So for example, here in this first 1-bit, we've got 1, 2, 3, 4 wave cycles squeezed in there. So that's a 4 hertz frequency. Okay. Next bit is also 4 hertz, but then here to represent the 0, we only have 2 peaks and 2 troughs. Okay. So in essence, what we're doing in this example on the right is we're representing 0 as a 2 hertz, okay, held for a certain period of time, and we're representing a 1 as 4 hertz, held for the same period of time as the 2 hertz. Okay. Okay. So this figure on the right encodes exactly the same bit string that we encoded on the left, or we did under amplitude modulation. Let's go back to our sound example here and see what that sounds like. Okay, and let's run this here. A little silence. Okay, let's run that again. One 0 0 0 1. Okay. Remember we talked earlier, how do we see or hear, quote unquote, frequency? Well, in light, our eyes interpret frequency as color. Okay. With acoustic signals, which is what we're getting when we play this demo, okay, we interpret frequency as pitch. Okay. Doubling the frequency, okay, is the same as raising the pitch by 1 octave. So the 1 bits here are 1 octave above the 0 bits because the frequency ratio is 2 to 1, or is doubling. Okay, so that's an example of frequency modulation. Okay. Moving forward, how many bits per second can we transmit using the encoding method shown at the bottom of the previous slide? In other words, the one we just looked at. Well, last time it was kind of easy because we had a direct relationship between the frequency and the data transmission rate. Because we were holding frequency constant. Didn't matter whether we were transmitting zeros or ones. The number of bits per second, the frequency of the wave, and therefore the number of bits per second was exactly the same. Here it gets a little trickier because our 0 bits are half the frequency of our 1 bits. But notice as I've laid out this graph here, the distance, okay, this distance is the same as this distance, which is the same as this distance. Okay, So the time periods are the same. Okay, it's simply a question of how many wave cycles can I squeeze in. Okay, and so apparently, looking at the graphic here, 2 wave cycles constitutes a 0 bit. 4 wave cycles at double the frequency, constitutes a 1 bit. Okay, so how much am I getting here? Well, let's skip forward to the answer. Again, it depends on the wave frequency, but also on the number of wave cycles per bit. Okay, so looking at the figure, a 1 bit is 4 consecutive cycles at 4 hertz. A 0 bit is 2 consecutive cycles at 2 hertz. Okay, so there's a 2-to-1 relationship with that, and therefore, since there's the elapsed time for both of those is the same. Okay, since it takes 4 cycles to represent the 1 bit. Okay, basically what I'm going to get is 1/4 of the carrier wave's frequency. Okay, and assuming 4 hertz, I'm getting 1 bit per second. Now, of course, if I was running this at, say, 4,000 hertz and 2,000 hertz, well, then it would be 1,000 bits per second. If I was running this at 4 megahertz and 2 megahertz, then I would be getting 1 megabit per second. So once again, it depends on the frequency, okay, but given the 4 hertz and 2 hertz here, I'm going to get an awfully low throughput of 1 bit per second. Okay. And if you're detecting a theme here of a direct relationship between carrier wave frequency and data transmission capacity, you are catching on quickly, and we'll nail that down a bit later. Okay, how can we increase transmission rate to 50 megabits per second? Well, I could kind of jump the gun on that. Okay, there's actually multiple ways to do it, but here's one way. Take the 1 bit and encode it in 4 consecutive wave cycles running at 200 megahertz. With the 0 bit, do 2 consecutive cycles of 100 megahertz. Okay, once again, a 2-to-1 variation. Okay, and what's our effective data throughput? Well, we've got 4 cycles at 200 megahertz, so 200 megahertz divided by 4 would be 50 megabits per second. Okay, so that's how we can get 50 megabits per second, simply push our frequencies up into the megahertz range. Okay. And obviously I can't give you an audio example of that because humans can't hear past 20,000 hertz. So megahertz is not something you're going to be able to, I'm going to be able to do a piano-based example of. Okay, last thing we can play with, and as I said, this is very different from the first two. Okay, something called phase shift modulation. Okay, and the key term here is shift. Okay. So, what do? Well, I take that pure sine wave and I just let it go in its usual direction, okay? And I use its usual pattern as a 1, okay? But if I want to follow up a 1 with a 0, what I do is I instantaneously jump from 0 to 180. Okay, what do I mean by instantaneously jumping from 0 to 180? Let's come back here to the beginning. Okay, if I'm going to do a 0 bit, I should start here and be going up, but instead what I'm going to do is jump from here straight to here. So instead of going up, I'll be going down. Okay, that's the shift in phase shift. Okay, so I should have been following that nice curve up, but instead I basically chopped off half of a cycle and started immediately on the down. Okay. Now, what I am actually detecting, or I should say what the receiver is actually detecting, is not so much the direction of this, it's the sudden change, the fact that we're not following the usual pattern. Okay, so we're following the usual pattern, that's a 1. We're continuing to follow the usual pattern, that's a 1. Oops, suddenly now we're not following the pattern. 180-degree shift, that's a 0. Oops, we changed back. Well, the 0 changed to a 1. Oops, we changed again. Now we're at a 0. We're still following the pattern, that's a 0. We're still following the pattern, that's a 0. Oops, we just shifted the pattern again, that's a 1. Okay, so the strange thing about phase shift modulation is it's not really the wave shape that represents the 0 or the 1. It's the change or lack thereof that represents the 0 or the 1. Okay, that makes it a very different animal Also, because humans don't really hear phase in the same way we hear frequency and amplitude, I don't have a nice little piano-based example that I can give you of what this would sound like. Okay. Trust me enough to believe that if I send this signal through a wire as electricity, I can construct a relatively cheap device at the other end that can detect these shifts and switch an output signal down one wire or another, representing a 0 or a 1, or or vary a voltage or not vary a voltage, representing a 0 or 1. I can do essentially the same thing with an optical device processor. So even though I can't give you a human ear example, trust me that optical devices or electrical devices that are reliable and fast can be constructed to recognize and interpret and react to these sudden shifts in phase. Okay. All right. How many bits per second can be transmitted using the encoding method shown at the bottom of the previous slide? Okay. Well, if I look at this signal and I back up and I look at the amplitude modulation signal, okay, I notice something. 1 cycle per time period. In amplitude modulation, what was different was how high was the peak. In phase shift modulation, what's different is, am I starting at 0 or am I starting at 180? Okay. But in each case, it's still 1 wave cycle per bit. Okay. And so the answer here to how many bits per second can I get is essentially the same as it was for amplitude modulation. Okay. It depends on the wave frequency. Since a single bit is encoded in each wave cycle, if I simply increase the number of cycles per second, increase the hertz, then I increase the number of bits per second. So, for example, if I use a 50 megahertz carrier wave, that would be fairly typical through, say, a copper cable, okay, then in theory I get 50 megabits per second, although once again, theory is one thing, practical considerations are something else. All right, one last slide I want to cover in this particular video, and we'll do later slides on another video. Thus far, what we have done is we have played with either amplitude, frequency, or phase to encode a single bit value. There's a 1, there's a 1, there's a 0, there's a 1, there's a 0. These are single bit values. Okay, and in the case of amplitude and frequency modulation, I varied one thing for one wave cycle to represent either a 0 or a 1. Okay, obviously it got a little more complicated with the frequency modulation, but still the same basic concept of in any one time period, 1 bit value. Okay. Well, what's so magic about 1 bit value? Well, we talked about that way back in an earlier chapter. There are various reasons that we like binary. One is that it's very easy to design and build electrical and optical devices that work just on 2 states. On or off, 0 or 1, high voltage, low voltage, whatever you want to call it. But that's not the only possibility. And one way to try to squeeze more data through one of these channels is to use a technique called multi-level coding. And the idea behind multi-level coding is this: in a single signal, say that 5 times fast, event, okay, or 1 wave cycle, rather than encoding just 1 bit value, how about 2 or 3 or 5 or 1500? Okay, well, let's start simple. Let's say instead of 1 bit value, I'm going to encode 2. Okay. Well, back in our earlier example of amplitude modulation, how did we do it here? We did a 1 bit was 10, and a 0 bit was 1. Okay, so 1 volt was a 0, 10 volts was a 1 bit. Okay, let's play with that a bit under multi-level coding to shove a little more data through here. What I'm going to do now is I'm going to have 4 different, instead of just 2 different voltage values, I'm going to get 4 different voltage values. Okay, I'm going to use 8, 6, 4, and 2. Okay, 8 volts is going to represent 2 1 bits. 6 volts is going to represent a that's going to represent a 1 bit followed by a 0 bit. 4 volts is going to represent a 0 bit followed by a 1 bit. We've got 2 examples of that here, this one and this one. Okay. And 2 volts is going to represent 2 0 bits. And we've got an example of that one right there. Okay. So I've got 4 different voltage ranges now, or 4 different voltage values, each of which represents a pair of bits. Okay. So here's that same bit string I had before, 11010001, encoded using amplitude modulation, but now instead of having 2 different amplitudes, I have 4 different amplitudes. Okay, and I don't since this cut up into pieces doesn't contain any 1 zeros, there's no example where it's 6 volts. The first 2 bits, because they're both 1s, is represented as 8 volts. The next 2 is 0, 1, so that's 4 volts. The next one is 0, 0, so that's 2 volts. And the next one's 0, 1, so that's 4 volts. Okay, so I'm going to send 8 volts, then 4, then 2, then 4. Okay, that's how I'm going to send those bits. Okay, so how does this increase my data transmission? Well, I'm still dealing with in this example, varying amplitude for 1 wave cycle. But whereas before each wave cycle encoded 1 bit, now I encode 2. What I've just done is doubled the data transmission capacity, assuming all other things are equal. Okay, so if the frequency of this wave was, say, 50 megahertz, under the earlier example of amplitude modulation, that gave us 50 megabits per second. But now, since I have 2 bit values encoded in each wave cycle, I'm getting twice the rate of data throughput, so that 50 megahertz carrier wave is now going to give me 100 megabits per second. Okay, I do have a sound example for this. What does this sound like? It sounds like this. Loud. Whoops, sorry, that started from the beginning again. Okay, that's those 4 sound levels. So what I've done is varied the amplitude of the sound to match these. Now you note, as I played that, it wasn't all that easy. You know, that loud one at the beginning was pretty easy to spot, but the volume difference between the next 3 was very slight. Now, if I was playing that to you live and asking you to call back, 11010001 as it came, do you think you could do that accurately? That would be pretty tough. Whereas the first example we did, where there was only 1 bit per wave cycle, and where I had a relatively large difference between the 0 and the 1 amplitude. Let me replay that one. Chances are, if you were writing down 11000101 whatever as I was playing that, you would probably be more accurate with that first one than you would with the second one. Okay, and this brings up a very important issue with respect to any sort of coding level, any sort of coding method, and it applies whether we're talking amplitude modulation, frequency modulation, or phase modulation. You want relatively large differences between things that represent a data value. Okay, in the early example of amplitude modulation, the difference was between 1 and 10. Well, that's a difference of 9. Okay, that's a big difference, and it's relatively easy to detect. It's easy for an electrical device to detect the difference between 10 and 1 volts. It's easy for, say, an optical device to detect the difference between, say, 10 and 1 lumens, or whatever the unit of power is we're talking about for optics. It's relatively easy for an acoustic device to detect the difference between 1 and 10 whatever decibels, or whatever the power unit is. But here in this example, we've only got a difference of 2, not 9 or 10, between our various values. That is much smaller and creates an accuracy problem for the receiving device. Okay, the electrical device has to be able to detect smaller variations in voltage and recognize them. Okay, ditto with the optical, ditto with your ear listening to that piano example. Okay, so we'll come back to this in a later video when we compare analog and digital. But I'm kind of setting you up for that for that discussion right now by noting that as we play with this multi-level coding game, okay, we wind up with much smaller differences that are significant as far as data. We are therefore more susceptible to transmission errors, and we have more difficulty constructing a device that's receiving this signal and can accurately decode the bit values that were stored in it. Okay? So that'll do it for this video.